Good evening, everyone. It may not be evening where you are, but it is where I am. So welcome to part 4 of this Unit 10 that is all about solution chemistry. The first thing that we're going to talk about is, actually both things we're going to talk about today have to do with, okay, great, so you've created a solution. You have dissolved a solute in a solvent. So what? What are some things that we might observe? And the first topic that we're going to talk about is something called conductance. When you create a solution, some solutions can conduct electricity. Some can, some can't. So conductance, or sometimes they'll use the word conductivity, is just a solution's ability to conduct electricity. In order for electricity to flow, charged particles of some kind are required. Now that's great for solutions that include what are called electrolytes. Electrolytes just means charged particles created by creating a solution. But some solutions, particularly ones that have covalent or molecular solutes, don't have any charged particles. Think about it. It's the difference between an ionic solute and a covalent solute. Ionic, ion. They have charged particles in them. So when an ionic compound dissolves, ions are released into the solution, into the solvent, and it can conduct electricity. When you dissolve something like sugar, for example, sucrose, it does dissolve in water, and we talked about why that is, because sugar is a polar molecule, so polar dissolves polar. However, just because it dissolves doesn't mean it will conduct electricity. Covalent solutes do not contain any ions. So sugar water will not conduct electricity. So any solution I give you can be put into one of 3 categories. It's a strong electrolyte, a weak electrolyte, or a non-electrolyte. A strong electrolyte would mean a solution that has lots of charged particles in it, lots of ions floating around. A weak electrolyte will have some charged particles, but not nearly as many. It will conduct electricity, but not as much. A non-electrolyte would be a solution that will not conduct at all. Now, if we were in regular school and I had this apparatus that I can use called a conductivity tester, it looks sort of like this. And I would take this light bulb, and it's hooked up to 2 electrodes, and I put the 2 electrodes down into various solutions. And what you'll notice is the one that says strong electrolyte lights up the light bulb nice and bright. Okay? That is because whatever's down in that beaker, that solution, contains a ton of ions floating around. Okay? So that would, an example of a strong electrolyte would be something like table salt, NaCl. Table salt dissolves in water and releases a ton of ions into the water. The middle one is a weak electrolyte. You'll notice the light bulb is lit up, but it's just sort of glowing dimly. Electricity is flowing, but there's not nearly as much. This would be something maybe like a solution of vinegar or one of our weak acids. So there are charged particles, but not nearly as many. On the far right, you've got a non-electrolyte. This could be something like sugar water. Okay? The solute does dissolve, but there are no ions floating around. Okay? So you might be asked to determine if something is a strong electrolyte. I probably at this point, not until you get to AP, those of you that are going to take AP, I probably would not ask you to identify a weak electrolyte, but I would ask you to determine whether something is strongly electrolytic or non-electrolytic. Okay? All ionic solutes, for the most part, are going to be strong electrolytes. Your covalent solutes are going to be non-electrolytes. So, that's just sort of something to know, is conductance. Okay, that some solutions will conduct electricity and others will not. Here's something else that we might observe when we create a solution. It's a topic called colligative properties, which just means any kind of physical property that is affected not by which solute did you dissolve, but how many particles will be present in the beaker once it dissolves. Okay, and so we're talking about when you've gone from a pure solvent like water and you've turned it into a solution. You've dissolved some kind of solute in it. Now this one, as I said, it does not matter what solute we're talking about. If anything dissolves, let's say in water, sugar, table salt, anything, any solution, we will see certain things happen. One of those things is we will see the boiling point go up. All right? Now, let's think about it. What is the boiling point of pure water in Celsius? 100 degrees Celsius, okay? Salt water, sugar water, any solution that you have dissolved a solute in water will not have a boiling point of 100. Salt water might have a boiling point of 104, 105. It doesn't matter what solute it is. Sugar water also has a boiling point above 100. Okay, now a solution of salt water is going to have a higher boiling point than a solution of sugar water, if they're at the same concentration, simply because dissolving table salt will release more particles into the water than sugar will. And we'll talk about how do you know how many particles are being released when a solute dissolves. We'll talk about that in a second. But what I want you to get here is that when you create a solution, the boiling point, no matter what the solute is, will be higher than what it was for the pure solvent. Something else that happens is that the freezing point goes down. Think about what the freezing point is for pure water in Celsius. It's 0. Salt water doesn't freeze at 0. Salt water might have a freezing point of -6. Okay? Again, any kind of solution, no matter what the solute is, the solution will always have a freezing point below the freezing point of that pure solvent. So let's talk a little bit about why that is. Okay, so again, this term colligative properties means that these are properties, things that change based on the number of particles. And the more particles there are, the greater the effect. Okay, so for example here, when I say how many particles are there, if we dissolve table salt in water, that will create, because this reaction in front of you is the reaction that occurs when something dissolves. You've got the solid form on the left and these ions in aqueous. Remember, aqueous just means dissolved in water. These are the ions that will be created when the dissolving process takes place. So sodium chloride produces 2 ions. Calcium chloride, on the other hand, look at this balanced equation. How many ions are on the product side? 1 calcium and 2 chlorides. That's 3 total ions on the right-hand side, 3 particles. So sodium chloride had 2, calcium chloride has 3. Aluminum chloride, again, look at the balanced equation here, has 4 particles on the product side. So of these 3, okay, if I made, I'll just pick a number. Let's say I made 2 molar, that's the concentration, 2 molar solutions of these 3 solutes. And I had them in 3 separate beakers. The one that produces the most particles of the solute will have the highest boiling point. It will also have the lowest freezing point. Aluminum chloride, because it produces the most number of particles, will have a boiling point, if I'm dissolving this in water, will have a boiling point the greatest above 100. It will have a freezing point the lowest below 0. Okay, so you might see some multiple choice questions like, which of the following solutes will have the highest boiling points? What you're looking for is how many pieces do these solutes break apart into? Now, what if your solute is covalent? Okay, think biology, guys. Look at this compound. What is it? It's glucose. It's sugar. Sugar dissolves in water. Covalent compounds do not ionize. They don't have any ions. So look at this reaction here. How many pieces are on the product side? We're going to count that molecule as a whole unit. Glucose dissolves and stays in just 1 piece. So let's say you're given a multiple choice question with now these 4 solutes. Sodium chloride, calcium chloride, aluminum chloride, and glucose. Which one has the highest boiling point above 100? It's still aluminum chloride. That glucose solution would have a boiling point above 100 because it's a solution, but it's going to be the least above 100 because it only produces 1 solute particle. So let's do a little bit of practice here. Okay? Let's say I asked you to, write the equation for how that solute breaks apart. All right, it breaks down into a lithium ion and a sulfide ion. Okay, now is that reaction balanced? No, it's not. There's 2 lithiums. So how many particles does lithium sulfide break down into? It breaks down into 3 particles. All right, let's look at another one. Gallium sulfate. All right, now what do you do if there's a polyatomic ion in there? Well, not to stress out, not to worry. Polyatomic ions don't break down. They stay together. Okay, so we could write out the balanced equation if we want, or we could just simply count the ions. There's 2 gallium ions and 3 sulfate ions. 2 plus 3, that solute would break down into 5 pieces, 5 particles. Okay, what about this guy? This is acetic acid. Now, guys, be careful. Look at those elements. I don't see a metal in there. That is not an ionic compound. That is a covalent compound. Now, it will dissolve. Acetic acid is vinegar, which will dissolve in water. But remember, covalent compounds are not going to break down into ions. It's just going to produce 1 particle on the product side. Okay, so if you have the note sheet in front of you, if you look at, there's some multiple choice questions in here. If you look at number 14, it's a multiple choice question. It says, which of the following aqueous solutions has the highest boiling point? And I'm going to write out on this little board here, I'm going to write out what the different options are. You'll notice that they all have the same molarity, but even if they didn't, that would be okay. Actually, one of them has a different molarity, but that's all right. Here are my options for solutes: potassium sulfate, ammonium nitrate, I've got hydrochloric acid, I've got magnesium sulfate, and the one at the bottom, I believe that is sucrose, table sugar, I believe. Okay, so these are my 5 options. Remember, we're looking at how many pieces, how many particles do these solutes break down into. So potassium sulfate, remember, polyatomics stay together as one unit. That's 3 pieces. Ammonium nitrate. There's 1 ammonium, 1 nitrate. That's 2 pieces. Okay, HCl is, that's an acid. We're going to talk about that in our next lesson. I know that those are 2 nonmetals, and so you think, oh, that's covalent, but we'll talk about this towards the end of the in the next lesson. This acid does actually split up into H plus and Cl minus, so that's 2 particles. Don't worry about it if you didn't know that. That's okay. Magnesium sulfate. Sulfate stays together. That's 2 particles. And then sucrose. I think that's sucrose. It's totally covalent. That's just 1. So again, the question says, which of the following has the highest boiling point? That's going to be potassium sulfate because it breaks down into the greatest number of particles. This would also be the answer if the question said, which one of these has the lowest freezing point? Okay. Now, let's talk a little bit about why this happens, okay? I think it's a little bit easier to understand in terms of why does the boiling point go up. So what you have in front of you in this picture, what's on the left is a pure solvent. Okay, let's say it's a container of water with a lid on it. So it's a closed container. And we've talked about this before. Anytime you have a closed container of a liquid, there are some of those liquid particles, but in gaseous form in the space above the liquid. When you have a bottle of water, even at room temperature, in the space above that water, there are water vapor particles up there. The image on the right is, let's say it is salt water. So those little brown particles, let's use those to represent solute particles. Okay, so pure solvent on the left, saltwater solution on the right. So here's what happens. It says, added solute particles get in the way at the surface of the liquid and make it harder for the solvent particles to escape. If you guys will notice, looking from the image on the left to the right, simply count how many particles are there in the gas form. In the picture on the left, up at the very top, I count 1, 2, 3, 4, I count 8 gas particles. On the right, I only see 6. Those solute particles form sort of a semi-permeable barrier that make the evaporation or boiling process of that solvent more difficult. It's like the solute particles almost form like a screen at the surface of the liquid. It's just more difficult for the solvent to get out into the gas phase. So heating water up to 100 degrees isn't going to cut it, because I can't get all of those water particles through that barrier. So I've got to raise the temperature a little higher to finally be able to get those solvent particles out into the gas phase. So the solvent needs more energy than it did before to get vaporized. So the boiling point goes up for that reason. The take-home message here is solute particles get in the way. Freezing point depression is kind of similar, okay? You can use the same take-home message. Solute particles get in the way. When we are trying to freeze a liquid, what we're trying to do is form intermolecular bonds, attractive forces between two liquid particles. Think about it. If you go from a liquid to a solid, that happens because liquid particles move closer together and they form a connection. They form a bond. Well, if you've got solute particles in there, they get in the way. Okay? It's like if you're trying to talk to your friend, but then this person keeps stepping in between the two of you, and you're just trying to have a conversation with your friend, but this random person just keeps interrupting your conversation and getting in the way. So freezing, pulling the energy away, because that's what happens in the freezing process, cooling down to zero, that's not going to cut it. That's not removing enough heat from the situation. I'm going to have to remove a little bit more than I usually do to finally get that bond to form between these two liquid particles. Okay? Now, hooray, get your calculators out. We're going to put a little math to this, and this is the final thing that we'll talk about. You have an equation in your notes, it's in bold, that looks like this. So we're not just going to talk about, well, how much, the freezing point goes down when you create a solution. We're actually going to calculate how low does it go. So the delta T in this equation, delta just means change. How much is the freezing point going to change? F stands for freezing. Okay, is the freezing point going to drop by 2 degrees, or is it going to drop by 22 degrees? All right, I'll come back to that little I in just a second. Little m is molality. Remember, that's moles of solute divided by kilograms of solvent. Kf is a constant. And in parentheses, it says it's given. If you guys will notice, you have a chart in your notes that has a whole bunch of different solvents listed. And for each one, you're told if the solvent is polar or nonpolar. You're given what is its normal freezing point. And then the next column has a Kf, a constant value. You don't have to memorize that. It's given to you. Okay, so Kf would be the constant for that particular solvent. That little I was what we were talking about a couple of slides back. How many solute particles does this solute break apart into? Okay, so you plug in I, M, and Kf, and you calculate how far is that freezing point going to drop. And you would do the exact same process for how much is the boiling point going to go up. The only difference is, instead of having a freezing point constant, look at your chart again, you'll notice I give you what is the normal boiling point, and I also give you a KB value for each solvent. Again, don't memorize, those are given to you. So let's look at an example. Okay, this is, I don't know if this one is in your notes. I believe that it is, but yes, I think it is. But look at the screen anyway. It says, calculate the boiling point and freezing point if 1.50 moles of aluminum chloride is dissolved in 1,200 grams of water. First of all, I would never give you a solute that doesn't dissolve in its solvent, but it's just good to check. Ionic, solute, water, yep, it's going to dissolve. So let me write up at the top that formula that we're going to use. Delta T equals IMK. Okay. So first things first, let me do this sort of off to the side. Let's calculate the molality. All right. It's 1.50 moles. Remember, molality is moles divided by kilograms. Okay, and that's going to give me a molality of 1.25, and I'll use that number throughout the problem. All right, so let's calculate how much is the boiling point going to go up. So delta T is my unknown. Little I is how many particles will this solute break down into? Aluminum chloride, that's going to break down into 4 particles. If you look at your chart in your notes, water is our solvent. The boiling point elevation constant, look all the way to the right, is 0.52. And the molality was 1.25. And when I put that in my calculator, I get that. Okay, now that's not the final answer. That is how much will the boiling point be going up? Well, what is water's typical boiling point? Usually it's 100. So 100 plus 2.6, my new boiling point is going to be 102.6 degrees. Be very careful when you're doing these practice problems in the notes. If water is not your solvent, you'll need to look up what is its usual boiling point. Okay, just a little heads up. All right, let's do the same thing for the freezing point depression. Okay, so the number of particles will be the same. Now the constant will not. Look in your chart. The freezing point constant is 1.86. The molality is still 1.25. I'm going to plug all of that in, and I'm going to get 9.3 degrees Celsius. But again, that's not my final answer. What is water's typical freezing point? It's 0, but it's going to fall. It's going to go below that, so here's my final answer. Okay? So that's how you do it. You'll need to use that chart when you're doing these practice problems. Okay? Let me just explain something real quick. We're almost done here. We've seen these phase diagrams before, okay, where you have temperature on the X, pressure on the Y, and you have solid, liquid, and gas regions. All I'm trying to illustrate with this diagram here is that when you go from a pure solvent to a solution, your freezing point and your boiling point, those change. We just went through that. Let me change color here. that red line, those two red lines, are to represent not a pure solvent, but a solution. If you look, and I'm starting right over here, okay, at 1 atmosphere, that's standard pressure. I'm going to follow this dashed line across and look where it hits that red line. That red line is like the new solid liquid barrier. If I follow that dot down to the x-axis, sorry, I'm not drawing very straight. Okay, that is the new freezing point. You'll notice it is below 0. Follow that 1 atmosphere dashed line over here to where it hits that new liquid to gas boundary. And I'm going to bring it down. That, on the x-axis, is the new boiling point. You'll notice it's above 100. Okay. I wouldn't ask you to draw anything like that. I just kind of wanted to show that to you. So guys, that is the end of the lesson. You should be able to answer all the questions in the homework at this point, the practice problems. Let's get through them, check your answers, and I look forward to seeing you guys at our next lesson. Take care.